So we looked at threshold population inversion, which is the minimum amount of population inversion, or the minimum rate at which electrons need to be drained from the lower level and occupied in the higher level, so that there is stable emission of laser light. Now we are going to try to derive a formal mathematical expression for this threshold population inversion rate. Now let us consider our laser setup, which consists of two mirrors M1 and M2 with reflectivities R1 and R2 separated by a distance L, which is filled of course with your active medium, your pump and so on. Reflectivity, in case you are doubtful, is like the percentage of incident light which a mirror reflects back. What percentage of the light incident on M1 does M1 reflect back, and similarly for M2. So yeah, we have two mirrors M1, M2, their reflectivities are R1 and R2. The distance between them, or the length of the reflector setup, is L. This is filled with your active medium and there is a pump and of course the usual things. Now let us say your photons are starting with intensity I0 from M1 and are traveling towards M2. So here are my photons. Let's say the initial spontaneous emission happened, it triggered some stimulated emission, and that stimulated photons are now at this point M1. They're going to start traveling towards M2 with intensity I0. So by the time they reach I0, it was experimentally determined that their intensity becomes I0 e raised to g minus a times L, where I0 is the initial intensity they started with, L is the length of the reflector or the active medium, and G and A are the rate of gain and loss per pass respectively. So the absorption coefficient is A and the gain coefficient is G. So gain coefficient as in the number of photons gained per unit length, and absorption coefficient A is the number of electrons absorbed as in the number of electrons which moved from lower level to higher level per unit length. So it was experimentally determined that by the time it completes one half trip, that is from left to right or vice versa, the intensity which was initially I0 becomes I0 e raised to gain minus absorption times L, because G is the gain and A is the loss, right? So effectively what is left with you is gain minus loss, and the relation was an e power relation. This, so now again it hits M2, it gets reflected back, and M2 has a reflectivity R2, meaning it will only reflect back R2 percentage of the light falling on it. So by the time it is reflected back from M2 and it is still here, the intensity has become R2 times I0 e raised to g minus a L, which is what you have here. After reflection, it has not started traveling back, the photon, but just post reflection, this is the intensity R2 times I0 e raised to g minus a times L. Now again this intensity photon is traveling back to M1. It becomes R2 I0 e raised to g minus a L into another e raised to g minus a L, because again experimentally it was determined that every time it covers one full length L, the intensity becomes a factor of e raised to g minus a L. So by the time it has come back to M1, it becomes R2 I0 e raised to twice of g minus a times L, and again once M1 has reflected it back, M1 has a reflectivity of R1, so it will reflect back R1 percentage of the incident intensity, so it becomes R1 R2 I0 e raised to twice g minus a times L. So what started out with an intensity of I0 after one full trip, round trip, ends up with this intensity R1 R2 I0 e raised to twice g minus a times L. So again, if you want stable emission, then sustained light for instead of flickering light or pulsing light sort of, if you want sustained light, then the intensity after one round trip should be greater than or equal to the initial intensity, of course, because if you are going to lose intensity along the way, then your light is going to fade and turn off at some point. So the intensity after one trip is over should be greater than or equal to your initial intensity. So we will quickly take a recap at how we arrived over here, and then we'll continue with the derivation. So this is the setup which I'm sure you all are familiar with by now. Your incident light starts with intensity I0. By the time it reaches here, it was discovered to have intensity I0 e raised to g minus a times L, where g and a are the gain and loss coefficients respectively. A stands for absorption. Now this is reflected back by M2 with reflectivity R2, so it becomes R2 I0 e raised to g minus a times L. It travels back all the way here, so again it becomes R2 I0 e raised to 2g minus a times L. Again reflected back by M1 with a reflectivity R1, it becomes R1 R2 I0 e raised to 2g minus a times L. So this should be greater than equal to the initial intensity I0. So in the worst case, it should at least be equal. So let's take that case and go on, because we want the minimum population inversion to be done such that the thing works, and that will be when the final intensity is equal to the initial intensity. So what are we doing here? Again, just for context, we are trying to derive population inversion, which is G, the loss coefficient, or the gain coefficient, G the gain coefficient. So anyhow, this is the expression we have. It should be equal to I0. So I0 and I0 here get cancelled. Your e raised to 2g minus al will be equal to 1 upon r1 r2. You're just taking the r1 r2 to the other side. Now why did g become g min? So generally we saw that the intensity should be greater than or equal to the initial intensity. Now the greater than equal to becomes equal to, because we are looking at the worst case scenario. I mean worst case, at least it should be equal. Then I'll get a stable light. If it is greater, well and good, but worst case it has to be equal, right? That's the logic. So because we're looking at the worst case, it becomes equal, and in that case the population inversion you create is the minimum amount of population inversion required to set up stable emission, and that is what we call threshold inversion, right? So because we're looking at that minimum, it becomes G min, but G and G min are effectively, they refer to the same quantity here. So anyhow, coming back, this is the expression we have. So since we have an E here, you take the natural log on both sides. Twice of G min minus A times L becomes natural log 1 upon R1 R2. So you keep G min alone on the left side and send everything to the right. It becomes A plus 1 upon 2L natural log of 1 upon R1 R2. So what is this expression or this derivation telling us? For sustaining oscillations inside the cavity, which means to make sure there is sustained photon activity inside the repeated amplification setup, and hence sustained beam of light, and not something that keeps flickering or not something whose intensity keeps going up and down. So to ensure such stable laser action, the minimum gain should be A plus 1 by 2L natural ln 1 upon R1 R2, where A is the absorption coefficient or the loss coefficient, L is the length of your setup, R1 and R2 the reflectivities of your mirrors. So this implies the existence of a minimum inversion where gain per pass equals loss per pass, and this is your equation for threshold population inversion.